Chapter 8 Combined Loading. Let's solve another example in foundation. So in this problem, we do have a 2 meters by 2 meters square foundation, which is handling a concentrated load of 120 kilonewton at its center of gravity and happen to handle two bending moments of mx equal to 20 kilonewton meters and an my 40 kilonewton meters. And if we neglect the weight of foundation itself, so we don't consider the weight of structure itself, we want to know what is the ratio of stress at point A to stress at point. So definitely because there is a concentrated load and a bending moment, so there is a combined loading for each of them. So we need to use superposition. So let's see how can we approach our problem. So if there is a concentrated load, as you can see at the center, that applies a 120 over the 4 meter area. That's a compressive stress applied at each point on beneath the foundation. And also there is, if you just consider my, you can easily see the effect of my, which is a push on point A. And also at mx, the effect of mx is a push again in A and push at point B. So if that's the case, we can write down the equation for stress at point A. That's a negative because of compression force over the entire area of foundation P over A, which is 120 over 4. A negative, again a push for x mx over mx over ix times ya, which is this distance, which is 1 meter. This is a square, so each dimension is 1 meter, 1 meter, 1 meter. And if you get the nature of again for my, it's again push at point A, so that's again a negative my over iy, my over iy times xa times this distance, which is again 1 meter. And if you add them up together, a 120 over 4 a meter square, that's a push. This is a push, this is a push. So that's a mx, which is 20 divided here. Just replace mx20 over here over 112 base cube height because it's a square, so that's 112 2 to the fourth, and negative my, which is 40 kilonewton meters, times xa, which is 1 meter, over 112 base cube height, which is 112 times 2 to the fourth, and that gives us a negative 30, negative 15, and additional negative 30. And if you add them up together, that's a negative 65 kilogram over meter squared. So sigma A is a compression stress at point A, and that's equal to 75 kilonewton over meter squared. Let's see what is this story in point B. So sigma at B my do not create any moment about point because it just passes through y-axis. As you can see, point B, it just passes through y-axis, so my cannot create any moment about that, but mx does. So again, we experience a push like a 120 for the entire area under any point under the foundation. Then if you look at the effect of mx on point B, that's a push to point A and a push of point B. So that's a positive because this is a push compression and this is a pull, which is a tension. So mx over ix times yb, which is again 1 meter due to the symmetry of the structure. And if you replace that with numeric value, it just gives us a negative 30, this time a positive, which is tensile 15, and it just gives us in a 50 a compression stress, which is still in safe zone, and it's not a foundation is not detached yet from soil. So then if we want to see sigma b is a still negative compression 15 kilonewton per meter square, and our problem is just asking what is the state of stress in terms of ratio of sigma a over sigma b, which is a 75, a negative 75 over 15. We can easily cancel out these negatives, and that gives us a 5, numeric value of 5. It means a stress at 5 at A is 5 times of stress at point B. Thank you. We'll solve more problems in stress states in combined loading.